GCSE Physics Higher Combined Science Trilogy 2021 paper solutions. You can click the link below to download the exam paper and follow through. Question 1. A student measures the potential difference across the battery and then puts the battery into the phone. What is the equation linking current, potential difference V, and resistance? The equation linking the three together is Ohm's law equation, and that's V equals IR, where V is the voltage, I is the current, and R is the resistor. Question 1.2. The current in the electronic circuit in the mobile phone was 0.125 amps. The potential difference across the battery was 3.9 volts. Calculate the resistance of the electronic circuit in the mobile phone. So we're given the current, which is 0.12 amps. We're given voltage. So now applying Ohm's law, V equals IR. And if I divide both sides by I, so the I here, we cancel I, and then we get V over I equals R. So now I'm going to substitute the value for V, I into the equation here. So V is 3.9 and I is 0.12. Therefore, if I compute that into the calculator, we get 32.5 ohms. Question 1.3. Write down the equation which links energy, power, and time. Power equals energy over time. If I multiply both sides by T, then the T here will be cancelled. Therefore, energy equals power times time. Energy equals PT. So either equation is fine. Question 1.4. The battery was fully charged when it was put into the mobile phone. The battery discharged when the mobile phone was switched on. The average power output of the battery as it discharged was 0.46 watts. The time taken to fully discharge the battery was 2,500 minutes. Calculate the energy transfer by the battery. Energy equals power times time. The power given is 0.46 and time is 2,500 minutes. We're going to multiply that by 60 to convert the minutes to seconds. And therefore, energy equals 69,000 joules. Question 1.5. What component does the circuit symbol shown in figure 2 represent? Well, the component is this component here, and this component is a thermistor. Question 1.6. The temperature of the component in figure 2 increases. The potential difference across the component remains constant. Explain what happened to the current in the component. I'm going to apply Ohm's law here. V equals IR, and if I divide both sides by R, I get I equals V over R. Because I'm dividing that by R, I'm dividing that by R, so I get R cancels out. I equals V over R. Now, as the temperature increases, the resistance will decrease. And if resistance decreases, then I, the current, will increase, because the relationship of the current is inversely proportional to resistance, which meant that if resistance decreases, the current will increase. Now, increasing the temperature will decrease the resistance of the thermistor. Question 2.1. A radioactive source emits alpha, beta, and gamma radiation. An alpha particle is the same as helium nucleus. How many times bigger is the radius of a helium atom than the radius of an alpha particle? Okay, here's the atom with its nucleus here in the center. If I split the nucleus and the atom apart and the nucleus radius here. To find the ratio, we just need to put the atom on top and the nucleus below, because nucleus is smaller than the atom. The radius of an atom is estimated around 10 to the power minus 10 meters, and the radius of a nucleus is estimated at 10 to the power minus 15 meters. 10 to the power minus 10 meters over 10 to the power minus 15 meters. So the 10 to the power minus 10 over 10 to the power minus 15, and I can rewrite it by splitting it up. That's 10 to the power minus 10 times 1 over 10 to the power minus 15. Now, 10 to the power minus 10 times 10 to the power 15. This is indices. Because they have same base, the base is 10, the base is 10, we usually add the power when we're multiplying them. So the common factor in the base is 10, and then we add the power, so minus 10 plus 15. Minus 10 plus 15 is 5, so that's 10 to the power 5. 10 to the power 5 is 100,000. So from the question, it's asking if it is less than 100 times bigger. No. Is it exactly 5,000 times bigger? No. Is it more than 10,000 times bigger? Yes, it is more than 10,000 times bigger. Question 2.2. Alpha particles can ionize atoms in the air. What happens to an atom when it is ionized by an alpha particle? So this is what we call helium atom. Helium atom has 2 protons, 2 neutrons, and 2 electrons. So this is helium atom, and this is how we write it in chemistry and physics. Helium nucleus is what we call alpha particle. Here is how we write alpha particle, 4 alpha 2, which means it's got only 2 protons and 2 neutrons, and it has lost its electrons. So alpha particle is helium atom that has lost its 2 electrons, and here it is. And this is how we write it in chemistry. 4, 2, He2 plus. The 2 plus indicating it has lost 2 electrons. And in physics, this is how we write it. 4 of 2 alpha. Both can be written either way in physics or chemistry. But mainly this is chemistry and that's physics. So this is an alpha particle coming in to strike an atom. An atom has an electron in its shell, and then this is what happens. That alpha particle will kick out the electron from the atom, and here's the electron being kicked out. The atom will become an ion with +1 charge because the number of protons is now bigger by 1 than the number of electrons. Atom have same number of protons and electrons. This ion will have 1 more proton than the electron because it has lost that 1 electron plus the alpha particle that came in the first place. So now from the atom we have formed a positive ion and we have lost 1 electron. So the atom here has become a positive ion there. The atom losing an electron. So this is the alpha particle plus the atom. This atom is neutral, same number of protons and electron. When it's being struck by alpha particle, the alpha particle will kick off 1 electron and the alpha particle, and then the atom will become a positive ion. That's the positive ion. Okay, from the selection, a neutron in the atom becomes a proton. No. The atom becomes a positive ion. Yes, the atom becomes a positive ion, which is that one. The atom gains a neutron? No. The atom gains a proton? No. The atom loses an electron? Yes, the atom loses an electron. Question 2.3. A spark detector is a device that can be used to detect alpha radiation. A spark detector works by alpha particles ionizing atoms in the air near a wire mesh. A large potential difference creates a spark when the air near the wire mesh is ionized. Suggest why a spark detector cannot detect beta radiation. The beta particle here, the beta radiation is only weakly ionizing. Spark is formed when an electron jumping from one point to another point. So no electrons to jump because beta does not ionize strongly like alpha particle. Ionize means electrons from shell are freed. Question 2.4. A teacher wants to demonstrate that the radioactive source emits alpha, beta, and gamma radiation. Describe a method the teacher could use. So the method is 1. To move the detector closer to the source, record the count rate, position the paper between the source and the detector, record a new count rate. Alpha radiation will not penetrate through paper. If the count rate with the paper is significantly less than without, then the source emits alpha radiation. Remove the paper and position the aluminum between the source and the detector. Record in the new count rate. Alpha and beta radiation will not penetrate through the aluminum if the count rate has significantly reduced compared with using paper, then beta radiation is present. If radiation penetrates through the aluminum, then the gamma radiation is present. The experiment should be repeated and mean result calculated because radioactive is a random process. Question 3.1. The wind turbine generates electricity to charge a battery on a boat. Name one other renewable energy resource that could be used on the boat to charge or to generate electricity. Another example could be solar. Question 3.2. The boat also has a generator that burns a fossil fuel. The battery can be charged by either the wind turbine or the generator. Give 2 reasons why this is useful. Point number 1, sometimes there is no wind, and so but the battery can still be charged using the generator. Or point number 2, when there is wind, less fuel is burned. Question 3.3. Explain one environmental impact of using fossil fuels to generate electricity. Okay, so the first common one is the carbon dioxide, CO2. That can increase global warming. Number 2 is the SOx and NOx gases emission. Example of a SOx gas is SO2 or SO3, and the NOx gas is NO2 or NO, and that can increase acid rain. And the acid you can get in this case are such as sulfuric acid, SO4, or nitric acid, HNO3, that's nitric acid. And this acid can be harmful to metals, corrode metal and things like that. And the third one, particulates or NOx, NOx gas emission, also can be harmful to a living organism. Question 3.4. The kinetic energy of the boat is 81 kilojoules and the mass of a boat equals 8,000 kilograms. Calculate the speed of the boat. So we're given kinetic energy, which is 81,000 joules. We're given a mass, 8,000 kilograms. We're looking for speed. So the kinetic energy is 1/2 mv squared. And if I multiply both sides by 2, I get 2E, that's the kinetic energy, equals mv squared. I need to divide both sides by m so that I can cancel that m. So 2E over m equals to v squared. So v squared equals to 2e over m, and then I need to square root both sides to get v, and that equals to plus or minus root 2e over m. But the speed is positive, so I'm only going to take the positive value. V, the speed in this case, is root 2e over m. Don't forget e is the kinetic energy. So I need to plug in those values. 2 times 81,000 over 8,000. So when I put that into the calculator, you get speed equals 4.5 meters per second. 3.5, as the boat passes over a wave, the gravitational potential energy of the boat increases by 19,600 joules. Mass of the boat is 8,000. Gravitational field strength equals 9.8 newtons per kilogram. Calculate the change in the height of the center of mass of the boat as it passes over the wave. As usual, we write down given. That means what you're given. We're given the gravitational potential energy, which is 19,600 joules. The mass is 8,000 kilograms, and the gravitational field strength is 9.8 newtons per kilogram. We need to find the height, h. Now you've considered the given. Now you want to think of a relationship between these variables. And the relationship we have is the gravitational potential energy, which is mass times gravitational field strength times change in height. Now, of course, we need to make the height the subject, change in height, so we need to divide both sides of the equation by mg. So that's what we've done. Divided by mg, divided by mg, so you get the mg cancels out here, so you get gravitational potential energy over mass times the gravitational field strength equals to change in height. Now we need to plug in the values, and therefore we can find h. Once we plug in the values into your calculator, you get change in height, or h, equals 0.25 meters. Question 4. A student determined the density of a cube made from bronze. The student used a balance to measure the mass of the bronze cube. Figure 5 shows the balance before the cube was added. It reads 4.2 grams. What type of error is shown on the balance? Okay, so this is a 1-mark question, and the answer to that is the 0 error. You may have systematic error, which is due to the apparatus being faulty before the experiment, and so you get the same error added all the time. Or you might get something called the 0 error. An example is a balance that is not zeroed correctly. As you can see From the diagram, it says 4.2 before the mass has been added. So you need to zero that. That means set that balance to 0. So if you didn't do that, that's called zero error. And that's the answer is 0 error. Question 4.2. How could the student get a correct value for the mass of the cube from the balance? Well, the student can get the correct value by resetting the balance to 0 grams before used. So reset the balance to 0 grams before use. Question 4.3. The student measured the length of the bronze cube using a vernier caliper and then using a micrometer. Table 1 shows the result. Complete the sentence. The result in Table 1 show that the vernier caliper and the micrometer have a different resolution. This is a micrometer, this is the value obtained, and this is a vernier caliper, and this is the value obtained. So these have a different resolution. You have to use the word resolution, otherwise you will not get the mark. What this is telling you is that this is giving you more detailed answer, so better resolution than that one. So we use in science resolution to describe a better detailed information. Question 4.4. The student had several identical coins. The volume of each coin was very small. The student added water to a measuring cylinder shown in figure 6. The student's reading the volume of water in the measuring cylinder. Give 2 changes the student should make to increase the accuracy of the volume measurement. Point number 1. The student should place the measuring cylinder on a horizontal surface. Number 2. View with eye in line with the level of the water. Like that, looking at the meniscus. Question 4.5. Describe how the student could use a displacement method to determine an accurate value for the volume of a single coin. 1. Add several coins to the measuring cylinder. 2. Measure the change in the water level in the measuring cylinder. 3. Divide by the number of coins added. Question 4.6. Old penny coins were made from a disc of bronze. New penny coins are made from a disc of a different metal. Figure 7 shows the disc of metal. Table 2 shows information about the disc used to make each coin. The disc used to make the old and the new coins have the same cross-sectional area. Calculate the value of x in table 2. Give your answers to 2 significant figures. So given the old penny, which is the mass, you got the density and the thickness. L is the thickness in this case. And new coin, again we got the mass, which is the same, and the density, we need to find the density for the new coin. Again, the thickness of that coin is given. So density equals mass over volume, and that's mv. Density has a symbol which is rho, but volume is cross-sectional area times the thickness. So volume equals A times L. Now I'm calling the thickness L. So rho, which is density, equals mass over volume, and volume is A times L. So that's density equals mass over volume. I multiply both sides by L to get rid of the L. So I get density times L. The length equals mass over area here, because the L cancel L here on the right hand side. So we got density times L equals mass over area, and we call that a constant K, because this is the same for both coins. It's the same value for coins 1 and coin 2. So we find that the density times thickness equals K. Therefore, the density for the metal 1 and its thickness is equal to density for metal 2 and its thickness. So that's why you got rho 1 L1 equals rho 2 L2. So I need to find rho 2. I need to make that the subject, and therefore I write rho 1 L1 over L2. So rho 2 is this one here. Rho 2 is this one, that's density, and rho 1 is this one. L1 is that one, divided by L2, this one. So I need to plug in the values. Rho 2 equals rho 1 8.9 times 0.16 over 0.17, and that equals 8.38. Therefore, density 2 for x will be equal to 8.4 grams per centimeter cube. And that is the answer we're looking for. So that's the value of x. Question 5.1. A TENS machine uses an electrical current to relieve pain. Figure 8 shows the electrodes of a TENS machine connected across an ankle, and the maximum power of the TENS machine is 240 milliwatts. The potential difference across the battery in the TENS machine is 2.5 volts. Calculate the maximum current from the battery. So we're given the power equals 240 milliwatts, and power equals to 240 times 1 over 1,000. Milli is 1 over 1,000, which is 10 to the power minus 3, and that's milli. So I'm changing the m to 1 over 1,000, which becomes 240 over 1,000. And 240 over 1,000 is 0.24 watts. The voltage given is 2.5 volts, and we're looking for the current. We know power equals current times voltage, and for current will be power over voltage. All I did was divide both sides by V. So I divided by V, divided by V, and then V cancels V, and then I've got current I equals to P over V. And therefore I need to plug in the value. The power is 0.24 divided by 2.54 voltage, and therefore the current is 0.096 amps. Question 5.2. Figure 9 is a sketch graph showing how the potential difference across the electrodes varies with time. A student concluded that there was an alternating potential difference across the electrodes. How does figure 9 shows that the student was not correct? Well, potential difference does not change direction, it's always positive. Alternating is a direction changing event, but potential difference is always positive because it does not change direction. Question 5.3. What relationship does this diagram shows? Well, the diagram here is showing a relationship between two variables, the potential difference and current, and this relationship is going through the origin. That is the origin here, or region. That's the origin, and therefore it's what we call Ohm's law, where V is equal to IR. V is directly proportional. So that means V is the potential difference here and I is the current. And from the relationship, V is directly proportional to I. Potential difference V is directly proportional to current I. When V goes up, the current goes up. When V goes down, the current goes down. Question 5.4. The figure 12 shows two more circuits that the student built using the battery from the TENS machine. We go as circuit A, which is this one here, and circuit B. I is the current, E is the electron. This is showing the direction of the current, and that's the direction of electron. R1 is a resistor, that's the voltage across the resistance. There's the ammeter measuring the current flowing through the ammeter. Likewise but this one is got one resistor, and this is got two resistors in parallel to each other. Same resistor from that, and again we got the same setup. The only difference is you got two resistors in parallel. The resistors all have the same resistance. Compare the readings on the voltmeter and ammeter in circuit A and circuit B. So now we are focusing on these second resistance, the circuit, because they have two resistances in parallel. So we're trying to convert them into single resistance so that we can compare it with this one. Now, in order to turn this into single resistor, we have to solve the parallel resistance equation, which is 1 over total resistance, that's a single resistance, equals 1 over R1 plus 1 over R1, because they are all in parallel. So common denominator is R1, so that's where you go R1, and then you add the numerator, 1 plus 1, that's 2. Now we need to invert this to find R total. If we invert that one, we have to invert that one. So that's R total equals R1 over 2. Now we know Ohm's law. V equals IR, and I is I2, and we got R to be R total, which is calculated. So if I make I to the subject, I get V over R total. So now we know I2 equals to V over R1 over 2, because R total is R1 over 2, and I can then write I2 equals, well, that 2 will go up, right? So that becomes 2V over R1. All right, so now let's look at these resistance for this one here. Okay, for this resistor for circuit A, we know V equals IR, and I1 which is the one flowing through here, is equal to V over R1. We also know that I2 equals 2V over R1. Right, we can see V over R1 here, that equals I1. So I'm going to replace the V over R1 here with I1, so therefore I2 equals 2I1. So the answer to the question 1. The voltmeter reading is the same in both circuits because the voltmeter here is measuring the voltage across that, and this voltage across that is still the same, but because they're in parallel, they will have the same voltage. So parallel resistors always have the same voltage, and because R1 is R1 here, again, they too will have the same voltage. So the voltmeter reading is the same in both circuits. The ammeter B reading is twice ammeter A reading. You can see ammeter B reading is I2. That's the ammeter reading, that's I2. And this is twice, I2 is twice I1. And that's what this is saying. The ammeter B reading is twice ammeter A reading. Question 6.1. An air source heat pump transfers energy from the air outside a building to increase the temperature of the air inside the building. Figure 13 shows an air source heat pump, and the compressor is connected to the main electrical supply. The pipe in the heat pump contains a substance called coolant. In the evaporator, energy is transferred from the air outside the building to the liquid coolant. The temperature of the coolant increases as it evaporates. Question 6.1 says, explain what happened to the internal energy of the coolant as its temperature increases. So the internal energy is equal to kinetic energy plus potential energy. So let U represent the internal energy, and that equals the kinetic energy, and kinetic energy is related to the temperature, and plus potential energy, and that's related to position or state. If the kinetic energy and potential energy both increases, then U, the internal energy, will also increases. As you know, the temperature is increasing, that means the kinetic energy is going to increase and U is going to increase. The internal energy will increase. Question 6.2. What name is given to the energy needed to change the states of the liquid coolant? Specific latent heat of vaporization or latent heat of vaporization. Here it is. This is what we're looking at. There's the liquid, and this is a point where you have, and there's no change in temperature, and that means the liquid and gas coexist together and the temperature is not changing even though more energy is being put in as you go along in time. Latent heat of vaporization is what we're referring to here. So the answer is only 1 mark, so you just need to say specific latent heat of vaporization or latent heat of vaporization. You don't need to draw the graph, I just drew the graph as an extra. Question 6.3. What happens to the mass of the coolant as it evaporates and becomes a vapor? Well, the mass will stay the same because we're referring to a closed system. Since it's a closed system, when the mass vaporizes, it stays the same because nothing goes in, nothing comes out. Question 6.4. The compressor increases the density and temperature of the coolant vapor inside the pipe. Explain why the pressure in the pipe increases. As the density and temperature increases, you will get more collisions of particles per second, a greater force per collision on the wall. 6.5. The condenser transfers energy from the coolant to the air in the building. When the total energy input of the heat pump system is 1560 kilojoules, the temperature of the air in the building increases from 11.6 degrees Celsius to 22.1 degrees Celsius. The efficiency of the heat pump system is 87.5%. The mass of the air inside the building is 125 kilograms. Calculate the specific heat capacity of the air in the building, giving your answer in standard form. So given, we always check what's given to us. We got the energy, which is 1560 kilojoules, and we've got the change in temperature, which is the final temperature minus initial temperature, and that is 21.1 degrees Celsius minus 11.6 degrees Celsius, and that gives us 10.5 degrees Celsius. Efficiency is 87.5%, which meant that it's 87.5 divided by 100, and that's 0.87. Mass is 125 kilograms. We need to find the specific heat capacity, which is C. So we know the formula for specific heat capacity. Energy equals mc delta theta, and E is m over delta theta to find C. So what we did was divide both sides by m delta theta. So divided by m delta theta. So m cancels m, delta theta cancels delta theta, and therefore C equals E over m delta theta. So we make C the subject here. That's what we're looking for. And we just plug in the values. 1560,000, because K is 1,000. So we turn it into 1,000 times the efficiency, because efficiency is not 100%. If it's 100%, we times it by 1, because it's not 100%, so we times it by the proportion, which in this case is 0.87, so 75. So that's 5 there. So we have to put 5 there to make sure. And so that's where that is. And then we divide it by the mass, which is 125 kilogram, and times it by the change in temperature, 10.5. And that gives us 1040 joules per kilogram per degree Celsius. And that can be written in standard form as 1.04 times 10 to the power 3 joules per kilogram per degree Celsius. Question 6.6. The air in the building gains 400 joules for every 100 joules of energy transferred from the mains electricity supply to the compressor. An advertisement claims that the heat pump system has an efficiency of 400%. Explain why the advertisement is not correct. So this question is 3 marks, so you're expecting 3 points. The first point is that the advertisement has ignored the energy input from the surrounding air. Secondly, so that the total energy input is greater than the energy supply from the electricity. And thirdly, the efficiency must be less than 100%. It can never be more than 100%.